Neptune is a blue planet. Not blue in the way that Earth is blue, not the bright, vivid, cloud-streaked blue of an ocean world seen from orbit. Neptune is a deeper blue, a dark, cold, almost violet blue, the colour of something submerged in very deep water, the colour of something that has never been warm, the colour that makes you feel the distance between it and the Sun even before you do the math. It is the most distant planet in our solar system, the last giant, the edge of the planetary family, hanging out there in the dark at an average distance of 30 astronomical units from the Sun, 30 times the Earth-Sun distance, orbiting so slowly that a Neptunian year takes 165 Earth years to complete. One spacecraft has ever visited Neptune. Voyager 2, launched in 1977, flew past it on August 25, 1989, giving humanity its only close-up look at the eighth planet. The flyby lasted a matter of hours. In those hours, Voyager 2 revealed a world of extraordinary storms, a magnetic field tilted at a dramatic angle, a system of faint rings, and a moon, Triton, that may be a captured Kuiper Belt object, with geysers that shoot nitrogen gas into its thin atmosphere. And then Voyager 2 continued onward, out of the solar system entirely, and Neptune was alone again. No spacecraft has returned to Neptune since. No mission is currently approved to go back. The farthest world in our planetary family has been visited once, briefly, by a machine the size of a small car, and it has been alone in the dark for over 3 decades. It remains one of the least understood major bodies in the solar system, a world about which we know tantalizingly little, whose deep interior structure is not well characterized, whose strange magnetic field is poorly explained, whose largest moon remains one of the most intriguing objects in the outer solar system. Now imagine sending people there, not a flyby in a small probe, people, human beings, in a crude spacecraft, travelling to Neptune, going into orbit, perhaps sending a lander to Triton, conducting the kind of extended, hands-on, improvised scientific investigation that only a human presence allows. The kind of mission that transformed our understanding of the Moon, that would eventually transform our understanding of Mars. A crude mission to Neptune. The idea sounds like science fiction, and in the sense that it is not something any space agency is currently planning or has ever seriously funded, it is, for now, in that category. But it is not beyond physics. It does not require new fundamental science. It requires engineering that is extraordinary, but not impossible, and decisions that are brutal, but not inconceivable. And thinking carefully about what it would actually require, not in a vague, inspiring way, but in a specific, honest, engineering-grounded way, reveals something important about both the scale of the outer solar system and the limits of what human beings can endure. The title of this video makes a specific claim. The first humans to reach Neptune would never come back. This is not speculation for dramatic effect. It follows from the actual physics and engineering of such a mission, from the timescales involved, from the fuel requirements for a return journey, and from what a transit of such duration would do to the human body and mind. The first people to stand at the edge of the solar system would stand there permanently, in every meaningful sense of that word, because the journey out would consume essentially everything that could be spared for the journey back. This video is the story of why the distance is so far in terms that go beyond the abstract number, why the human body, a machine designed by 4 billion years of evolution for life on the surface of Earth, deteriorates in ways that the journey's duration would amplify into genuine catastrophe, why the fuel and propulsion requirements for a return trip are not merely challenging, but essentially incompatible with the mission architecture needed to get there at all, and why, despite all of this, there is an argument, not a simple or comfortable one, but a real one, that such a mission might someday be worth undertaking anyway. We start with the distance, the real distance, not the number, but what it means. Chapter 1. How far Neptune actually is, the number that breaks intuition, 4.4 billion kilometers. That is the average distance between Earth and Neptune. The precise figure varies as both planets orbit the Sun at different rates. Earth takes a year, Neptune takes 165 years. So the actual distance ranges from about 4.3 to 4.7 billion kilometers, depending on where both planets are in their respective orbits. For our purposes, 4.4 billion kilometers is a reasonable working figure. 4,400 million kilometers. It is, like all numbers describing solar system distances, simultaneously precise and completely useless to human intuition. Our brains did not evolve to navigate distances like this. The largest distances we can genuinely feel, the kind that lodge in your sense of scale and stay there, are perhaps a few hundred kilometers, a drive from one city to another, a transatlantic flight. Even the moon, at 384,000 kilometers, is something we can place in our mental model of the solar system without truly feeling it. The Earth-Sun distance of 150 million kilometers is where numerical descriptions begin to dissolve into abstraction. So let's try to make 4.4 billion kilometers real. First comparison, light travel time. Light, the fastest thing in the universe, traveling at 299,792 kilometers per second, takes approximately 4.1 hours to travel from the Sun to Neptune at average distance. From Earth to Neptune, averaging out the orbital geometry, it takes roughly 4 to 5 hours for light to make the trip. If you sent a message to a crewed Neptune mission and asked, "Are you alright?" you would wait 4 hours to discover whether it was received, and another 4 hours for the reply to reach you. 8 hours for a single exchange. That communication delay is not just operationally difficult, it is psychologically severing. It means any crew at Neptune is isolated from Earth in a way that no previous space mission has experienced, because there is no such thing as real-time communication at that distance. Second comparison, the Voyager 2 transit time. Voyager 2 was launched in August 1977 and arrived at Neptune in August 1989. 12 years. And Voyager 2 was not aimed directly at Neptune. It used a planetary gravity assist trajectory, swinging past Jupiter in 1979, Saturn in 1981, and Uranus in 1986, each flyby bending its path and adding velocity. The gravity assist were essential to reaching Neptune in 12 years. Without them, on a direct trajectory from Earth, even with Voyager 2's initial velocity, the transit time would have been considerably longer. 12 years, with the benefit of 4 planetary gravity assists, is the benchmark for how long it takes an uncrewed probe launched with 1970s technology to reach Neptune. Now consider what 12 years means for a crewed mission. 12 years ago, from when you are reading this, where were you? What was happening in your life? How much has changed? 12 years is an enormous fraction of a human life. It is the difference between childhood and adulthood for many people. It is the span of a career, a marriage, a child growing up. A crew that departed Earth for Neptune on a 12-year transit would arrive, having spent a substantial portion of their adult lives in a spacecraft, knowing that the journey back would require at least as long, meaning they would not return to Earth until approximately 25 years after departure. But 12 years is actually an optimistic figure for a crewed Neptune mission, because a crewed spacecraft faces very different constraints from an uncrewed probe. Voyager 2 weighed about 722 kilograms, a crewed spacecraft capable of sustaining multiple people for years, providing life support, carrying sufficient food and water and medical supplies, and performing scientific operations at Neptune would be orders of magnitude more massive. The heavier the spacecraft, the harder it is to achieve the velocities needed to make the transit in any reasonable time. The planetary alignment that enabled Voyager 2's gravity assist trajectory occurs only once every 175 years. The next comparable alignment will be around 2150. A mission that cannot wait for that alignment, using direct trajectories or less favourable gravity assist opportunities, would have a longer transit time. Conservative estimates for a crewed Neptune mission using reasonably advanced propulsion put the one-way trip at somewhere between 7 and 20 years, depending on the propulsion technology and the launch window used. Third comparison, the distance in terms of our current fastest spacecraft. The New Horizons probe, launched in January 2006 and the fastest spacecraft ever launched from Earth, reached Neptune's orbit in August 2007, roughly 18 months after launch. But New Horizons was not attempting to stop at Neptune. It was flying through at high velocity, using a Jupiter gravity assist to maintain its speed for the journey to Pluto. A spacecraft that needs to slow down and enter Neptune orbit, rather than simply fly through, must carry the propellant to decelerate from interplanetary cruise velocity to orbital velocity, which dramatically reduces the final velocity achievable given the mass constraints of launch. The fundamental problem is captured by what rocket engineers call the tyranny of the rocket equation. The Tsiolkovsky rocket equation, derived in the late 19th century by Russian mathematician Konstantin Tsiolkovsky, describes the relationship between the change in velocity a rocket can achieve and the ratio of its initial mass, including propellant, to its final mass, after the propellant is expended. The equation is exponential in its unforgiving character. To double the velocity change achievable, you must square the mass ratio of propellant to payload. As the required velocity change increases, the propellant mass grows faster than the payload mass, meaning that the vast majority of a spacecraft's launch mass ends up being propellant rather than useful payload. For a crewed Neptune mission, the required velocity changes are enormous. You need delta V, change in velocity to leave Earth orbit, delta V to adjust course during the transit, and, critically, delta V to slow down on arrival and enter Neptune orbit rather than flying through. If you want to also return to Earth, you need delta V to leave Neptune orbit and delta V to slow down on arrival at Earth. Each of these maneuvers requires propellant, and the propellant for each maneuver must itself be launched from Earth, meaning it adds to the mass that all the other propellant must accelerate. The numbers compound rapidly into something daunting. For any mission architecture that attempts to use conventional chemical propulsion, the same technology that took humans to the moon, the propellant mass required for a crewed Neptune round trip is so enormous as to be essentially impractical with any foreseeable launch vehicle. The Saturn V, the most powerful rocket ever flown, could lift about 130 tons to low Earth orbit. A chemically propelled crewed Neptune round-trip mission would require thousands of times that mass in propellant in low Earth orbit before departure. The engineering of assembling that mass in orbit, essentially constructing a small city's worth of rocket fuel in space, is not obviously feasible on any near-term timescale, which is why any serious discussion of a crewed Neptune mission eventually arrives at the same conclusion. You need better propulsion. Nuclear propulsion specifically, either nuclear thermal propulsion, which heats propellant by passing it through a nuclear reactor for significantly higher efficiency than chemical rockets, or nuclear pulse propulsion, which uses a series of nuclear detonations to drive the spacecraft forward. Neither of these technologies is currently operational in space. Both have been studied seriously. And even with nuclear propulsion, the mission timeline and the propellant requirements are extreme enough to make the return journey a question that has a very specific and very stark answer. But we need to talk about something else before we get to the return journey. We need to talk about what happens to the human body on the way there. Because the distance, the transit time, and the fuel constraints are all part of why the crew would never come back. But the body is perhaps the most personal part of that story. Chapter 2. The propulsion problem, getting there without dying on the way. Let us be specific about what it would actually take to propel human beings to Neptune in a timeframe compatible with human life. The current gold standard for deep space mission planning, the kind of planning that serious space agencies and research institutions actually do, suggests that a crewed mission to the outer solar system would require a transit time of at least 7 years one way, under the most optimistic near-term propulsion assumptions, and potentially 2 to 3 times longer with more conservative assumptions. 7 years is already an extraordinary duration. Let's look at what it would take to achieve it. Chemical propulsion, as we established, is essentially out of the question for the full transit. The specific impulse, the measure of fuel efficiency for rocket propulsion, of the best chemical rockets is simply too low to make the mass fractions workable for a multi-year crewed mission to Neptune. The spacecraft would need to be almost entirely propellant, with essentially no room for crew, life support, scientific payload, or any of the other elements that make a crewed mission meaningful. The first realistic technology is nuclear thermal propulsion. In a nuclear thermal rocket, a nuclear reactor heats a propellant, typically liquid hydrogen, to extremely high temperatures, and the heated hydrogen expands through a nozzle to produce thrust. The specific impulse achievable with nuclear thermal propulsion is roughly twice that of the best chemical rockets, which means the mass fraction for any given velocity change is dramatically more favourable. Nuclear thermal propulsion was seriously developed by the United States in the NERVA program, which ran from 1955 to 1972, and tested nuclear thermal engines that achieved performance well beyond any chemical rocket. The program was cancelled before flight testing, primarily for political rather than technical reasons. A spacecraft using nuclear thermal propulsion could achieve the Neptune transit in perhaps 7 to 12 years, depending on the specific propulsion system performance, the launch window, and whether the mission could use gravitational assists from Jupiter or other outer planets. This is still an enormous duration by any human standard, but it is at least in the range of something that human beings could theoretically survive, even if surviving it would require extraordinary physical and psychological preparation and infrastructure. The next step up is nuclear pulse propulsion, the most powerful form of rocket propulsion that does not require currently non-existent physics. The concept, first studied seriously in the Orion project in the late 1950s and early 1960s, involves detonating a sequence of nuclear bombs behind a large pusher plate at the rear of the spacecraft, with each detonation propelling the craft forward. The Orion project, conducted at General Atomics with participation from physicists including Freeman Dyson, produced detailed engineering analyses suggesting that a nuclear pulse spacecraft of sufficient size could reach Neptune in a matter of months to a few years, potentially reducing the transit time to 2 to 4 years. The specific impulse achievable with nuclear pulse propulsion is many times that of nuclear thermal propulsion, and the thrust available is enormous, equivalent to thousands or millions of conventional rocket engines firing simultaneously. A Freeman Dyson-style Orion vessel of the scale, contemplated in the original studies, could accelerate to a significant fraction of the needed velocity quickly enough that Neptune transit times of 2 to 3 years were considered realistic. But nuclear pulse propulsion has a specific and currently insurmountable obstacle: the Partial Nuclear Test Ban Treaty of 1963, which prohibits nuclear detonations in space. The treaty was signed by the United States, the Soviet Union, and the United Kingdom, and has since been adhered to by most spacefaring nations. Amending or withdrawing from the treaty to enable nuclear pulse propulsion in space is theoretically possible, but practically very difficult, and no serious political movement toward doing so has emerged. Setting aside pulse propulsion, there are other emerging propulsion technologies that might eventually enable faster Neptune transits: nuclear fusion drives, which use controlled fusion reactions to produce enormous specific impulse and thrust; antimatter propulsion, which offers the theoretically highest possible specific impulse, but requires the production and storage of antimatter in quantities far beyond current capability; and advanced solar sails or laser sails, which could reach high velocities in the inner solar system but lose effectiveness at the extreme distances of the outer solar system. All of these remain research concepts rather than operational technologies, with development timescales measured in decades at minimum. For any near-term mission, meaning within the next few decades, nuclear thermal propulsion with some form of gravity assist trajectory is the most realistic option, and it produces a one-way transit time of roughly 7 to 15 years. For the purposes of the rest of this video, let us use 10 years as a round figure. A 10-year transit is brutally long by human standards, but it is conceivably survivable. It is long enough, however, to cause serious, possibly irreversible damage to the human body through a combination of factors that we need to examine carefully. Chapter 3: What a decade in space does to a human body. The slow catastrophe. The human body was not designed for space. This is a fact so basic and so frequently glossed over in discussions of deep space exploration that it deserves explicit, detailed examination. We are products of roughly 4 billion years of evolution optimized for life on the surface of a planet with a specific gravity, a specific atmospheric composition, a specific magnetic field, a specific daily light cycle, and a specific ecosystem of microorganisms. Remove any of these conditions and the body begins in specific and measurable ways to deteriorate. The International Space Station has given us the most detailed data set we have on long-duration human spaceflight, and the findings are sobering. ISS crew members on standard 6-month tours of duty return to Earth measurably different from when they left. Not just tired or psychologically adjusted, physically different, in ways that are biological and structural, and that require months of rehabilitation to partially reverse. Now consider not 6 months but 10 years. Bone density loss. In microgravity, bones lose density. The mechanism is straightforward. Bones maintain their density through mechanical loading, the compressive and tensile forces that gravity and muscle activity place on the skeleton. Remove gravity, remove those forces, and the body interprets the skeleton as excess mass and begins to reabsorb it. Osteoclast activity, bone resorption, exceeds osteoblast activity, bone formation, and the result is progressive bone density loss. On the International Space Station, bone density loss proceeds at roughly 1 to 2% per month in the weight-bearing bones, the hips, spine, and legs, even with aggressive exercise countermeasures. Astronauts typically spend 2 to 3 hours per day exercising specifically to counteract this loss, and they still lose significant bone mass on a 6-month tour. The bones of an astronaut who has been in space for 6 months are measurably weaker than before departure, and full recovery of bone density after landing takes many months to years. On a 10-year mission, with current countermeasures, the bone density loss would be catastrophic. Even optimistic estimates, based on current exercise countermeasures and pharmacological interventions that might be developed, suggest that a crew member would arrive at Neptune with bones dramatically weaker than those of any person who has ever lived. Standing up, walking, surviving any impact, these would become genuinely dangerous activities. The solution that engineers envision for very long-duration missions is artificial gravity, rotating the spacecraft or a portion of it to produce centrifugal acceleration that substitutes for gravitational loading on the skeleton. A rotating habitat that produces even 0.5 to 1 g of effective acceleration would substantially slow or prevent bone density loss. The engineering requirements for a rotating habitat are significant. The habitat must be large enough that the rotation rate is low enough to prevent motion sickness, and the structural requirements of rotation impose mass and complexity penalties, but they are not physically impossible. If a crewed Neptune mission were designed with a rotating habitat providing artificial gravity throughout the transit, bone loss would be dramatically reduced. This is likely to be a non-negotiable design requirement for any multi-year crewed deep space mission. The point remains relevant because the engineering and mass constraints of including a rotating habitat add to the already enormous complexity and cost of the mission, and because even with artificial gravity, other physiological challenges remain. Radiation. The invisible killer bone density is a problem that engineering can partially solve. Radiation is harder. On Earth, we are protected from the full flux of cosmic radiation by 2 shields: Earth's magnetic field, which deflects charged particles, and Earth's atmosphere, which absorbs ionizing radiation that gets through the magnetic shield. In deep space, beyond the protection of Earth's magnetic field and with no atmosphere whatsoever, the radiation environment is dramatically more hostile. The primary radiation sources for a deep space crew are galactic cosmic rays, high-energy particles accelerated to near light speed by distant astrophysical events like supernovae, and, closer to the Sun, solar energetic particle events, which are bursts of radiation associated with solar flares and coronal mass ejections. Galactic cosmic rays are particularly challenging because they are omnidirectional, highly penetrating and constant. Unlike solar energetic particle events, which can be to some extent shielded against and which the crew can shelter from during acute events, galactic cosmic rays cannot be effectively blocked by any passive shielding of practical mass. The dose received from galactic cosmic rays in interplanetary space beyond the magnetosphere is estimated at roughly 300 to 900 millisieverts per year, depending on solar activity. For comparison, radiation workers on Earth are limited to 50 millisieverts per year, and the lifetime dose limit for NASA astronauts has historically been set to limit cancer mortality risk to no more than 3% above baseline. The annual dose in deep space, on the most conservative estimates, approaches or exceeds NASA's career limit in a single year. Over a 10-year transit to Neptune, a crew would accumulate radiation doses that would, by current standards, massively exceed any acceptable exposure limit. The increased cancer risk from such exposure is substantial. Estimates vary, but a 10-year deep space transit could increase lifetime cancer mortality risk by 5 to 15% or more. Additionally, high-energy cosmic rays damage the central nervous system, not just through cumulative carcinogenic effects, but through direct disruption of neural tissue, potentially causing cognitive decline, memory impairment, and behavioral changes. Studies of mice exposed to simulated cosmic ray environments have shown neural damage and cognitive deficits after relatively short exposures. Active radiation shielding, creating an artificial magnetic field around the spacecraft to deflect charged particles, has been proposed and studied. The engineering challenges are significant. Creating a magnetic field strong enough to deflect high-energy cosmic ray particles requires superconducting electromagnets operating continuously for years, consuming substantial power. Current prototypes and theoretical analyses suggest that active magnetic shielding could reduce cosmic ray exposure by perhaps 30 to 40%, which helps but does not eliminate the problem. Water is an effective passive shield for lower energy radiation, and mission designs frequently propose surrounding the crew habitat with water tanks and other hydrogen-rich materials to provide a radiation buffer. But the mass required for effective passive shielding against the highest energy cosmic rays is prohibitive. You would need meters of water around the entire habitat, adding tens or hundreds of tons to the spacecraft mass. Some combination of passive and active shielding will be necessary, and no currently available approach reduces the radiation dose to levels that fall within current acceptable limits for a 10-year mission. The practical implication is this: any crew sent to Neptune would be accepting a significant and quantifiable reduction in life expectancy in exchange for making the journey. This is not a hypothetical risk to be managed with better technology. It is a hard physical reality of the current radiation environment of interplanetary space, and while future technological developments may partially mitigate it, they are unlikely to eliminate it entirely for a mission of this duration. Cardiovascular deconditioning. The heart, like all muscles, adapts to the demands placed on it. In a gravity environment, the heart must pump blood upward against gravity to supply the brain and upper body, a continuous demanding task that keeps the cardiovascular system in a state of active exertion. In microgravity, this demand disappears. Fluid redistributes headward. The heart, sensing what it interprets as fluid overload in the upper body, reduces blood volume by excreting fluid. The vascular system adapts to the reduced demand. The heart itself begins to lose mass and to become less efficient at pumping blood against a gravitational gradient. The consequence is that when a microgravity-exposed astronaut returns to a gravity environment, the cardiovascular system is inadequate for the demands suddenly placed on it. Blood pools in the legs. The heart cannot pump sufficient blood upward. Standing up can cause orthostatic intolerance, the inability to maintain blood pressure and consciousness when upright, severe enough to incapacitate the person until the cardiovascular system readapts. ISS crew members returning from 6-month missions often require assistance to stand and walk for days to weeks after landing. For a crew that has spent 10 years in microgravity, even with a rotating habitat providing partial gravitational loading, the cardiovascular deconditioning upon arrival in any gravity environment would be extreme. At Neptune's moon, Triton, surface gravity is approximately 0.08 GE, much less than Earth but still a gravitational loading the crew would need to adapt to. More critically, if any part of the mission involved spending time in environments with significant gravitational loading, even a fraction of Earth's gravity, the cardiovascular preparation would be a critical concern. Muscle atrophy. Like bone and the cardiovascular system, skeletal muscle atrophies in microgravity. Without the constant work of supporting the body against gravity, muscle mass decreases progressively. The rate of loss, even with exercise countermeasures, exceeds what can be prevented with current technology. An astronaut on a 6-month ISS mission loses a significant fraction of lower body muscle mass despite exercising several hours per day. Over 10 years, the loss would be devastating without more effective countermeasures than currently exist. A rotating habitat that provides artificial gravity would largely address the muscle atrophy problem, in the same way it would address bone density loss. The loading provided by artificial gravity would maintain the demand on skeletal muscle that prevents atrophy. This reinforces the argument that any multi-year crewed deep space mission must include artificial gravity as a design requirement, not a nice-to-have feature, but an essential medical requirement. The immune system, long-duration spaceflight dysregulates the immune system in ways that are not fully understood. Studies of ISS crew members show changes in immune cell populations, alterations in cytokine production, and reactivation of latent viruses, including herpes viruses that the immune system normally keeps suppressed. The mechanisms behind these immune changes are multiple: stress hormones, the altered microbiome in a closed spacecraft environment, the radiation environment, and possibly the loss of the normal daily light cycle that regulates circadian rhythms. A crew member whose immune system has been progressively dysregulated over 10 years of spaceflight would be significantly more vulnerable to infectious disease and potentially to cancer, both from the accumulated radiation damage and from the reduced immune surveillance that helps identify and eliminate precancerous cells. Maintaining crew health over 10 years in an isolated spacecraft without the full resource of Earth's medical system is one of the most significant challenges of the mission. Vision and intracranial pressure. One of the most concerning discoveries from ISS research in the past decade is that a significant fraction of long-duration spaceflight crew members experience vision changes, including blurred vision and measurable changes to the structure of the eye. The leading hypothesis is spaceflight-associated neuroocular syndrome, SANS, in which the redistribution of fluid to the head in microgravity, the same headward fluid shift that causes the cardiovascular changes, increases intracranial pressure and causes structural deformation of the optic nerve and the back of the eye. The changes are in some cases permanent. On a 10-year mission, the cumulative effects of elevated intracranial pressure could be severe. Vision impairment, structural changes to the brain, and neurological consequences of sustained elevated pressure are genuine concerns for multi-year microgravity missions. Again, artificial gravity substantially mitigates this risk by restoring the normal fluid distribution of a gravitational environment, but it does not eliminate it entirely, and any periods of the mission spent in microgravity, during orbital, maneuvering, or during the transit phases where the rotating habitat might be temporarily non-operational, represent periods of elevated risk. The cumulative picture of what 10 years in deep space does to the human body is not one that allows easy optimism. The combination of radiation damage, cardiovascular deconditioning, bone density loss, muscle atrophy, immune dysregulation, and neurological changes produces a person who, upon arrival at Neptune, is measurably and in some respects permanently different from the person who left Earth. The mission to Neptune does not end these effects. It continues them, potentially for the years of orbital operations and surface exploration at the destination. And then, if a return journey were contemplated, it would continue them for another decade of transit. By the time a Neptune crew member returned to Earth, if they returned at all, they would have spent roughly 20 years in the deep space environment. The physiological consequences would be severe enough that some of the effects, particularly the radiation-induced cancer risk, the structural neurological changes, and potentially the bone architecture changes, would be irreversible. They would return as different people, in a physical sense, from the ones who left, assuming they survived the return journey to begin with. Chapter 4. The Point of No Return. Why coming back is harder than going now, we arrive at the crux of the title. Not just the journey would be very difficult, which is true, but specifically why the crew would, in a real and operational sense, not be coming back. And this argument is not primarily about the physiological effects, as serious as they are. It is about the physics of propulsion and the arithmetic of fuel. The return journey from Neptune is not just the same trip in reverse. It is, from a propulsion standpoint, significantly harder than the outbound journey, for a reason that is elegant in its brutality. When you travel from Earth to Neptune, you are travelling away from the Sun, and in doing so you are trading kinetic energy for gravitational potential energy. The Sun's gravity slows you down as you move away from it. When you travel from Neptune back to Earth, you're falling toward the Sun, gaining kinetic energy, which means you arrive at Earth with too much velocity and need to slow down. And slowing down requires fuel, just as speeding up does. The propellant required for the return trip, the delta V for leaving Neptune orbit, for any course corrections during the transit, and for the deceleration needed to enter Earth orbit rather than flying past it, is comparable to or exceeds the propellant required for the outbound journey. This means the spacecraft arriving at Neptune, after a 10-year transit, must still have enough propellant aboard to make the return journey. The propellant for the return must have been carried from Earth through the entire 10-year outbound transit, waiting unused. Carrying propellant for the return journey means the spacecraft must be heavier at departure, which means it needs more propellant for the outbound journey, which makes it heavier still in the familiar exponential spiral of the rocket equation. For most serious mission architectures, the massive propellant required for a complete round trip, accounting for the outbound transit, orbital insertion at Neptune, extended operations at Neptune, departure from Neptune, and return transit, is so large that it either requires an impossibly massive initial launch or requires in situ resource utilization, manufacturing propellant at Neptune from local resources. The latter option is theoretically possible, but requires bringing a complete chemical processing plant to Neptune, running it on energy sources available at 30 astronomical units from the Sun, where solar power is roughly 900 times weaker than at Earth, and producing propellant from the local environment, which at Neptune means extracting hydrogen from the planet's atmosphere or from ice on Triton. The prospect of in situ propellant production at Neptune is not absurd, but it is technically ambitious to a degree that, combined with the already extreme challenge of reaching Neptune at all, makes a fully self-sufficient round-trip mission essentially unfeasible with any near-term technology. Let us put specific numbers on this, because numbers are more honest than vague descriptions of difficulty. A crewed spacecraft to Neptune needs, at minimum, to provide living quarters, life support, food and water, medical systems, scientific equipment, and communication systems for multiple people for at least 10 years. A rough minimum mass estimate for such a spacecraft stripped to essentials is something on the order of 50 to 100 metric tons of non-propellant mass, the actual useful payload. This is already a very optimistic figure. Real mission designs tend to be heavier. For a nuclear thermal propulsion system with a specific impulse of about 900 seconds, roughly twice the best chemical rocket, and a one-way delta-v requirement of about 15 to 20 kilometers per second, for a Neptune transit with orbital insertion, the rocket equation gives a mass ratio of roughly 5 to 8. This means for every 1 kilogram of payload delivered to Neptune orbit, the spacecraft needs to depart Earth orbit with 5 to 8 kilograms, the difference being propellant. For 75 tons of payload, the departure mass is 375 to 600 tons. This must all be assembled in Earth orbit, from launches from Earth's surface. Now add the return journey. The return from Neptune requires a similar delta-v budget, which means another factor of 5 to 8 in mass ratio for the return propellant. But the return propellant must be carried from Earth as well. It is additional mass in the spacecraft from the beginning, which must be accelerated during the outbound transit, which increases the outbound propellant requirement, which increases the departure mass further. Working through the compounded rocket equation for a complete round trip with nuclear thermal propulsion, the departure mass from Earth orbit for a minimally equipped crewed Neptune mission becomes enormous, in the range of thousands of tons. This exceeds the total mass humanity has ever launched to orbit in all of history by a substantial margin. Even with assembly in orbit over many years of launches, it represents a logistical challenge that dwarfs the Apollo program, the Space Shuttle program, and the International Space Station program combined by several orders of magnitude. This is why the return journey does not fit in the mission architecture, not because the physics forbids it in principle, but because the mass and cost requirements of including full return propellant are incompatible with any mission budget and launch infrastructure conceivable in the near to mid-term future. The first crewed Neptune mission, if it ever happens, will almost certainly be designed as a one-way mission, not as a choice about the crew's fate, but as a consequence of the physics that no amount of engineering creativity can fully evade. The mission that sends the first humans to Neptune will send them permanently. They will set up a base, conduct their science, communicate their findings back to Earth over the 8-hour radio delay, and live out their lives in the orbit of the most distant planet. Some of them may be able to return to Earth on future supply missions, if any future supply missions are funded and sent. But the core crew, on the first mission, with the propellant budget that the first mission can realistically carry, would not come back. This is not a dramatic interpretation, it is the operational arithmetic of the mission. End of Part 1. Part 2 continues with what actually awaits at Neptune, the communication and psychological architecture of permanent deep space habitation, the governance and social structure of an isolated permanent crew, and the question of whether this mission should ever be attempted and why some argue it must be. Chapter 4. Continued. The mission architecture and the honest math. Let's be more specific about what a realistic first crewed Neptune mission would actually look like, because the general arguments about propellant mass ratios, while accurate, do not fully convey the specific choices that mission planners would face and the specific reasons that those choices lead, almost inevitably, to a one-way configuration. A crewed Neptune mission of any kind would need to be justified by scientific objectives that could not be achieved by an uncrewed spacecraft. Otherwise, the enormous cost and risk of sending humans would be impossible to defend. The scientific case for humans at Neptune is actually strong in specific respects. Neptune and Uranus are the least understood planets in the solar system. Both are classified as ice giants, a poorly defined category distinguished from the gas giants Jupiter and Saturn by their different composition, which includes significant amounts of water, ammonia, and methane ices, in addition to hydrogen and helium. The interior structures of both planets are not well characterized. Their magnetic field geometries, both have fields dramatically tilted relative to their rotation axes, are not understood. Their atmospheric dynamics produce wind speeds among the highest in the solar system, and Triton, Neptune's largest moon, is likely a captured Kuiper Belt object with its own internal heating, its nitrogen geysers, and the possibility of subsurface liquid, making it one of the more scientifically interesting bodies in the outer solar system. A crewed mission to Neptune could do things that no robotic mission could realistically accomplish: deploy a long-term seismometer network to characterize the interior structure, collect atmospheric samples by descending through the cloud layers with a reusable atmospheric probe directed by human operators in real time, conduct systematic geological and geochemical surveys of Triton's surface with the flexibility and improvisation that human investigators provide, and establish the kind of sustained, multi-year observational baseline that answers questions that brief flyby missions cannot address. The mission would almost certainly be designed in phases. An initial crew would be sent with the primary scientific objectives and the supplies needed for a several-year stay. Subsequent supply missions, potentially uncrewed, given the extraordinary expense of crewed missions, would replenish consumables and possibly bring additional crew members or return some of the original crew. The architecture would resemble, in its broad strokes, the model of research stations in Antarctica, where the initial expedition establishes a base, and subsequent missions build on and sustain that base over time. The crucial difference from Antarctica is that there is no practical rescue option. If a crew member at an Antarctic research station becomes critically ill, an emergency evacuation flight can reach them within hours to days. If a crew member at a Neptune orbital station becomes critically ill, the nearest help is 10 years away. The mission's medical infrastructure must be capable of handling any medical emergency that might arise, entirely autonomously with no external support. The crew's physician, who would need to be part of the crew, would need to be capable of performing emergency surgery, managing critical care, and treating any disease or injury without the option of transfer to a higher care facility. This self-sufficiency requirement extends to every system on the spacecraft and the station. A malfunction that on an Earth-based facility would be fixed by calling a specialist with the right expertise, and parts must be diagnosed and fixed by the crew using whatever tools and knowledge they have on hand. The spacecraft's systems must be designed for maintainability and repairability by generalists, not specialists, and the crew must collectively have the breadth of expertise to address failures across engineering, medical, biological, computational, and physical domains. This is a significantly different training and selection requirement from any existing astronaut program. The supply mission cadence is another critical planning variable. If supply missions, carrying food, water, spare parts, medical supplies, and potentially fuel, can be launched every 2 to 3 years and reach Neptune in another 7 to 10 years, the crew can be sustained indefinitely without being physically capable of returning to Earth. The crew does not need to come back if the supplies come to them, and the supplies do not need to carry human beings in both directions to be effective. An uncrewed supply spacecraft, optimized for cargo rather than life support, is dramatically lighter and can therefore be cheaper to launch and faster to arrive than a crewed return vehicle. This asymmetry, crewed outbound, uncrewed supply, is the specific architecture that makes a one-way mission viable in a way that a round-trip mission is not. The crew accepts permanent residence at Neptune in exchange for the ability to do science there that could not otherwise be done, supported by a supply chain from Earth that sustains their lives and work indefinitely. This is not simply a death sentence with a scientific justification. It is a model of exploration that has precedent on Earth. The permanent research stations in Antarctica are inhabited by people who go there knowing they will not stay forever, but who, during their tours, operate in an environment where immediate return to the outside world is not possible. The Neptune mission is this model taken to its extreme logical conclusion, but what makes it permanent, rather than merely long duration, is a combination of the round-trip propellant problem and the physiological changes that accumulate during the outbound transit. Even if the propellant could be provided, even if future technology or in situ resource utilization made the return journey physically possible, the crew that arrives at Neptune after 10 years of deep space transit would be so physiologically different from a person who could simply board a return vehicle and survive the transit back that return would be meaningfully different from what the word implies for a person who has spent a decade in space. They would return to a planet they had left when they were years younger, to a world that had changed profoundly in their absence, to families who had aged a decade without them, to bodies that would need years of rehabilitation to function in Earth gravity, to social networks, cultural contexts, and professional environments that had moved on. The return would not be a restoration. It would be an arrival at a place that was familiar in memory but not in reality, a planet that was technically home but that would feel, in every practical sense, like arriving somewhere new. The first humans to reach Neptune would never truly come back, even if they made it to Earth again. The people they were when they left would be gone. The world they knew would be gone. The mission would have changed them permanently and irrevocably, in ways that no amount of rehabilitation or readjustment could fully reverse. This is the other dimension of the title's claim. Not just that the physics prevents return, but that the journey itself makes return in any meaningful sense impossible. Chapter 5. What actually awaits at Neptune. The science that justifies everything. Before we can properly evaluate whether sending permanent human residents to Neptune is a rational undertaking, and before we can feel the full weight of what those residents would be giving up and gaining, we need to understand what Neptune and its system actually are, because the scientific case for going there is not merely another planet to check off the list. It is a genuine, deep, unanswered set of questions about the structure of the solar system and the physics of planetary formation that no remote sensing instrument, no brief flyby, and no series of uncrewed orbiters can fully address. Neptune is an ice giant. This categorization, separate from the gas giants Jupiter and Saturn, is relatively recent in planetary science, and it reflects a genuine physical distinction. The interiors of Jupiter and Saturn are dominated by hydrogen and helium, the most abundant elements in the universe, compressed by the planet's enormous mass into exotic states, metallic hydrogen, dense fluid hydrogen, that generate their powerful magnetic fields and drive their atmospheric dynamics. Neptune and Uranus are different. Their interiors contain substantial amounts of water, ammonia, and methane, under conditions of extreme pressure and temperature, compressed into states of matter that do not exist anywhere on Earth, and that we understand only partially from theoretical models. The question of what the interior of Neptune actually looks like, in terms of temperature gradients, convective patterns, the boundary between different compositional layers, and the specific physical state of the material at each depth, is one of the most important unanswered questions in planetary science. Our current best models of Neptune's interior are constrained almost entirely by three observational inputs: its mass, derived from gravitational effects on passing spacecraft, its radius, derived from occultations and direct measurement, and its magnetic field, measured by Voyager 2 during the 1989 flyby. Three numbers for a planet whose interior spans tens of thousands of kilometers and whose dynamics operate across billion-year timescales. The uncertainty in our interior models is enormous. Neptune's magnetic field. Something is very wrong, and we don't know what the magnetic field of Neptune is, one of the most genuinely anomalous features of any planet in the solar system. Earth's magnetic field is generated by convection in the liquid iron outer core and is roughly aligned with the rotation axis, tilted by about 11 degrees, which is why compass north differs from geographic north but by a navigable margin. Jupiter and Saturn also have magnetic fields roughly aligned with their rotation axes. Uranus and Neptune are completely different. Neptune's magnetic field is tilted approximately 47 degrees from its rotation axis. Additionally, the center of the magnetic field, the point from which the dipole field appears to emanate, is offset from the planet's center by roughly 0.55 Neptune radii. The field is not only drastically tilted but also dramatically off-center, in a way that no other known planet exhibits to this degree. Uranus shows a similar extreme tilt and offset. This configuration has no accepted explanation. The models that produce magnetic fields from planetary interiors, essentially all versions of dynamo theory, predict fields that are more or less aligned with the rotation axis unless there is something very specific about the interior structure that breaks the axial symmetry. For Neptune's field to be as tilted and offset as it is, something in the interior convection pattern must be fundamentally different from what produces aligned dipoles in Earth, Jupiter and Saturn. One hypothesis involves the physical state of the deep interior. Water under the extreme pressures inside Neptune transitions into what is called supersonic water, a state in which the oxygen atoms form a crystalline lattice, while the hydrogen ions flow freely, behaving simultaneously like a solid and a liquid. Supersonic water would have very different electrical conductivity properties from the deep fluid layers inside gas giants, potentially driving the dynamo in a different way and producing the bizarre off-axis field we observe. But this hypothesis is based on laboratory experiments at extreme pressures and on computer models, not on direct observation. A permanent crewed station at Neptune would be positioned to conduct exactly the kind of sustained, systematic observations needed to constrain interior models in ways that no brief flyby could. A long-term magnetic field survey, measuring temporal variations, secular changes, and the fine structure of the field over years or decades, would provide the data needed to discriminate between competing interior models. Combined with seismic measurements, if a probe could be deployed into Neptune's atmosphere to measure pressure waves, and with detailed atmospheric dynamics observations, a multi-year crewed mission would dramatically advance our understanding of how ice giant planets work, not just Neptune, but the entire class of planets, which are thought to be the most common type of large planet in the galaxy beyond our solar system. Triton, the most geologically active moon in the outer solar system. Neptune's largest moon, Triton, is in many ways even more scientifically interesting than Neptune itself. It is one of only a handful of objects in the solar system where active geological processes have been directly observed, and it orbits Neptune in the retrograde direction, opposite to Neptune's rotation, which is the clearest evidence that it was not formed in the Neptunian system but was captured from the Kuiper belt at some point in the past. The orbital mechanics of Triton's capture, and the tidal heating that results from its non-circular orbit, makes Triton one of the most geologically active and thermally complex bodies in the outer solar system. Voyager 2's brief flyby in 1989 revealed Triton's surface in fleeting detail. A nitrogen ice surface, with dark streaks extending downwind from what appeared to be active geysers. Plumes of dark nitrogen gas ejected from below the surface, carried by Triton's thin nitrogen atmosphere in consistent directions that created visible streaks on the ice. The geysers of Triton are not powered by internal radioactive heating, as volcanic features on some moons are. They appear to be powered by a mechanism unique to Triton: solar heating of the nitrogen ice surface. The subsurface nitrogen is warmed by solar radiation filtered through a thin, transparent layer of ice, reaches a temperature slightly above the sublimation point, and explosively vaporizes through weak points in the overlying ice. Even at 30 astronomical units from the Sun, where solar flux is roughly 900 times weaker than at Earth, this mechanism produces geysers that Voyager 2 photographed from above. But the more intriguing possibility is that Triton has something deeper going on. Its surface shows a peculiar cantaloupe-like terrain, with rounded depressions and ridges that suggest convective overturn of icy material driven by internal heat. Its density, measured at about 2.061 grams per cubic centimetre, significantly higher than pure ice, implies a substantial rocky component in its interior. The combination of internal rocky material, tidal heating from its retrograde orbit, and the complex chemistry possible in a body that was once a Kuiper belt object raises the question of whether Triton might have, somewhere in its interior, a liquid water ocean. A subsurface liquid water ocean on Triton would place it in the same category as Europa, Ganymede, and Enceladus, the class of ocean worlds that astrobiologists consider among the most promising targets for the search for extraterrestrial life. The energy sources are there, tidal heating from the orbital interaction with Neptune. The liquid medium might be there, a subsurface ocean sustained by that heating. The chemistry of a captured Kuiper belt object, formed in a different part of the solar system and processed over billions of years, would be rich and complex. Whether life exists in a Triton ocean is entirely unknown, but the question is scientifically legitimate. Investigating Triton at the level needed to answer this question requires more than an orbiter sending back remote sensing data. It requires seismometers on the surface to detect internal activity. It requires detailed spectrographic analysis of the surface chemistry in the geyser plumes to understand what is being erupted from below. It requires long-term monitoring of the surface to detect changes that occur on timescales of years rather than hours. And eventually, if the evidence warrants it, it might require drilling through the ice to sample the subsurface material directly. All of these activities are possible for a crew stationed in Neptune orbit. None of them is practical for a brief flyby or even for a robotic orbiter operating alone, because the distance means that real-time control of surface operations is impossible. Every command from Earth takes 4 hours to arrive, and every image or reading the surface probe sends back takes 4 hours to reach Earth for analysis. The lag means that robotic surface operations on Triton, controlled from Earth, would proceed at a pace so slow that years of mission time would be consumed in the back and forth of commanding, executing, and evaluating. A crew in Neptune orbit, with communications to Earth but with direct command authority over surface assets, could operate on timescales of hours rather than years. Neptune's atmosphere, the most violent weather in the solar system. Neptune's atmosphere generates wind speeds of up to 2,100 km per hour, the fastest measured winds on any planet in the solar system. The Great Dark Spot observed by Voyager 2, an anticyclonic storm system comparable in relative scale to Jupiter's Great Red Spot, had disappeared by the time Hubble Space Telescope observed Neptune in 1994. New dark spots have appeared and disappeared since. Neptune's atmospheric dynamics operate on timescales that require continuous, long-term monitoring to understand. Timescales that a flyby mission measures in hours, and even an orbiting robotic mission struggles with because of the communication delay. The source of Neptune's extreme atmospheric activity is itself a puzzle. Neptune receives only 1/900th of the solar radiation that Earth does. Its internal heat source, residual heat from formation and from radioactive decay, is modest compared to Jupiter's. And yet it produces the most violent atmospheric dynamics in the solar system. The mechanism must involve some combination of internal heat flux, the chemistry of the atmosphere, and circulation patterns that our current models do not correctly predict. Solving this problem requires multi-year atmospheric monitoring with direct sampling capability that a crewed mission could provide. The scientific case for a crewed Neptune mission, in short, is not simply compelling, it is hard to overstate. Neptune and Triton together represent some of the most scientifically important and most poorly understood objects in the entire solar system. They are at the frontier of what we know about planetary physics, ocean worlds, and the outer solar system's chemistry and dynamics. A permanent human presence at Neptune would represent one of the greatest accelerations of scientific knowledge in the history of planetary exploration. Chapter 6. The Communication Problem. 8 hours between question and answer. Let us talk about the silence. Not the silence of space, which is total and constant regardless of distance. The specific silence of the communications delay. The 8-hour gap between sending a message and receiving a reply that would define every interaction between a crewed Neptune mission and everyone on Earth. 8 hours one way, 8 hours back. Every question answered in 16 hours. Every decision that requires input from Earth taking the better part of a day. Every emergency that might benefit from outside advice arriving at mission control 4 hours after the situation has already evolved, beyond whatever advice might have been offered. This is not just operationally challenging, it is psychologically and sociologically transformative. It changes the nature of the relationship between the crew and Earth in a way that has no real precedent in the history of human exploration. Consider how current space missions work. The ISS crew communicates with mission control in near real time, a communication delay of less than a second, functionally instantaneous. When something goes wrong on the ISS, flight controllers on the ground are watching telemetry in real time, can immediately diagnose the problem from the data stream, and can provide instructions within seconds. The ISS crew operates with the full cognitive and experiential resources of Earth's most capable aerospace engineers immediately available to them at all times. They are never truly alone. Even Mars, at maximum distance of about 401 million kilometers, has a one-way communication delay of about 22 minutes, long enough to be frustrating but short enough that a conversation, conducted over an hour or two, remains possible. A crew on Mars that encounters a serious technical problem can call home, describe the situation, receive input from Earth's technical teams, and implement a solution within a few hours, the delay is manageable. At Neptune, with a one-way delay of 4 hours, a conversation becomes essentially impossible. The crew sends a message describing a problem. 4 hours later, Mission Control on Earth receives it and begins analysis. 4 hours after that, their response arrives at Neptune. 8 hours have elapsed. During those 8 hours, the crew has already had to make decisions, implement solutions, and live with the consequences, all before receiving any input from the most knowledgeable people on the problem. By the time Earth's advice arrives, the situation will have already been resolved one way or another. The practical implication is that a Neptune crew must be completely self-reliant in all decision-making. Not self-reliant in the way that a mountain expedition is self-reliant, where the team makes its own decisions but knows that rescue is possible and emergency communication is available. Self-reliant in the absolute sense, the crew's decisions are the final decisions, period. There is no appeal to higher authority. There is no calling in expertise that is not physically present on the spacecraft. There is no crisis that can be managed from Earth in real time. This has specific implications for crew selection and training. Every crew member must be capable of contributing meaningfully to decisions outside their primary specialty. The physician must understand enough structural engineering to evaluate a critical component failure. The geologist must understand enough medical science to assist with a complex procedure. The pilot must understand enough of the scientific mission to make judgment calls about redirecting resources when unexpected discoveries warrant it. The depth and breadth of cross-training required for a Neptune crew would exceed anything in the current astronaut training program. But the deeper implication is psychological and sociological. 8 hours of silence means that Earth, everything the crew left behind, everyone they love, every cultural and social context that defined them before departure, is permanently unreachable in any emotionally meaningful sense. You can send messages to Earth. You can receive messages from Earth. But the conversation, the real-time exchange of emotion and reassurance, and shared experience that constitutes human connection, is gone. What remains is correspondence. Letters sent across time, each delayed by a third of a day. This is a kind of isolation that no previous space crew has experienced. ISS crews have difficult psychological experiences with the isolation of 6 months in low Earth orbit, even though they can make essentially real-time phone calls home, watch live television, and participate in ongoing Earth events through the internet with minimal delay. They are isolated from Earth's physical environment while remaining connected to Earth's information and social environment. A Neptune crew would be isolated from both. Their connection to Earth would be a stream of messages, delayed by hours in each direction, that constitutes a kind of asynchronous pen-pal relationship with everyone they have ever known. The psychological design of the mission, the provision of meaningful work, of social structure within the crew, of sufficient autonomy to feel genuine agency, of sufficient cultural connection to Earth to prevent the profound anomie that total isolation can produce, is as important as the physical design of the life support system. A crew whose psychological cohesion fractures, whose motivation collapses, or whose individual members deteriorate into depression or paranoia, poses an existential threat to the mission that no amount of technical redundancy can address. The spacecraft can have backup systems for every critical function. There is no backup system for a crew that has stopped functioning as a crew. Chapter 7. The Psychology and Social Architecture of Permanent Isolation. The study of human psychology in isolated and confined environments is a relatively young field, but it has produced a body of knowledge that is directly relevant to understanding what a Neptune mission crew would experience. The analog environments that researchers have used to study long-duration isolation, Antarctic winter overstations, nuclear submarines on extended patrols, simulated Mars habitats, and the Mars 500 mission, in which 6 crew members spent 520 days in a sealed module simulating a Mars mission, have consistently revealed patterns that any Neptune mission planner would need to take seriously. The first pattern is the third quarter phenomenon. Studies of Antarctic winter over crews who spend extended periods of complete physical isolation at stations like Concordia or Amundsen-Scott South Pole Station consistently show a specific temporal structure to psychological deterioration. The first quarter of the mission tends to be characterized by high motivation, novelty-driven engagement, and effective social functioning. The second quarter often shows some adaptation fatigue but remains manageable. The third quarter, when the mission is past its halfway point but the end is not yet in sight, is where depression, irritability, interpersonal conflict and motivational collapse most frequently peak. The fourth quarter often shows recovery as the end approaches. For a Neptune mission, the third quarter phenomenon would occur approximately 7 to 8 years into a 10-year outbound transit. 7 years into a voyage in which Earth is a set of delayed messages rather than a real place, in which the destination has been approaching for years without arriving, in which the daily environment is an unchanging series of metal corridors and recycled air. This is when the psychological architecture of the mission would be under maximum stress. The design implications are significant. The mission timeline should incorporate specific planned activities that provide psychological markers, events that divide the 10-year transit into meaningful segments rather than a featureless stretch. Planned experiments with meaningful milestones, cultural events marked and celebrated, communication packages from Earth timed to arrive at psychologically important moments, the scheduling of variety in the crew's experience within the constraints of the spacecraft environment. Long-duration mission psychology research has shown that these relatively simple interventions can meaningfully reduce the severity of the third quarter phenomenon. But the deeper challenge is interpersonal, small. Groups confined in tight quarters for years develop complex social dynamics that cannot be fully managed by any intervention. Research on Antarctic winter over crews, submarine crews, and space station crews consistently shows the emergence of groupthink, expeditionary disease, a pattern of social withdrawal and communication breakdown, and interpersonal conflicts whose apparent causes are trivial, but whose emotional intensity reflects the accumulated stress of prolonged confinement. In a crew of, say, 6 or 8 people, the loss of effective social functioning in even 1 or 2 individuals, through depression, personality change, or interpersonal breakdown, can compromise the functioning of the entire group. The selection criteria for a Neptune crew would be more demanding than those for any previous space mission, and they would need to prioritize psychological resilience and social compatibility at least as highly as technical competence. The standard astronaut selection process identifies people who are highly competent, highly motivated, and capable of functioning effectively under stress. These are necessary but not sufficient conditions for a 10-year mission. The additional requirements are the ability to function effectively in extreme uncertainty for years without external validation, the capacity to maintain genuinely warm social relationships with the same small group of people for a decade without the relief valve of external social contact, the psychological resilience to absorb the permanent loss of everything on Earth, the deaths of parents, the aging of children, the transformation of friendships, without losing motivation or stability, and the philosophical capacity to find meaning in a life that has, by choice, permanently separated itself from the world that gave it context. This last requirement deserves its own examination because it is the most unusual and in some ways the most important. The loss of Earth as an anchor. Human psychological well-being is, to a considerable extent, anchored in continuity. The sense that there is a stable world, a home, a culture, a network of relationships, to which one can return or on which one can rely for support provides an ongoing psychological foundation that most people never have to notice because they never lose it. The possibility of return, even when return is not imminent, provides a form of security that is different from, and more fundamental than the security of knowing that the spacecraft's life support is functioning. A Neptune crew that has accepted permanent separation from Earth has given up this anchor. Not temporarily, the way an astronaut going to the ISS for 6 months gives it up temporarily, permanently. The world they knew, the streets they grew up on, the restaurants they liked, the ease of walking into a building and encountering other human beings, is gone from their lives and will remain gone for the rest of their lives. New things will happen on Earth, new discoveries, new politics, new cultural shifts, and they will learn about them through delayed messages, but they will not be participants. They will be observers of Earth through a time-delayed window, inhabitants of a separate world that happens to share the same solar system. Humans have managed comparable situations before. People who emigrate to completely new countries, who abandon their birth cultures and social networks, who live for decades or forever separated from their places and people of origin, these people can and do live full and meaningful lives. The key psychological element that enables this is not the maintenance of connection to what was left behind, because that connection inevitably weakens. It is the construction of a new and genuine life in the new place, with new relationships, new purposes, and new sources of meaning. For a Neptune crew, the new life would be constructed in the most extreme isolation imaginable. The new relationships would be the relationships within the crew, a group of people who were selected for compatibility and who knew, before departure, that these relationships would be among the most important in their lives. The new purpose would be the scientific mission, which would need to be not just intellectually compelling, but genuinely, deeply meaningful to each crew member in a way that sustains them across years of difficulty. And the new place, Neptune orbit, Triton's surface, the edge of the solar system, would need to become home in a psychological sense, not just a location. Research on what makes isolated environments bearable and on what makes them unbearable consistently points to the same factors: perceived control and agency, meaningful work with visible outcomes, genuine social connection to a group whose other members are also psychologically healthy, sufficient space and privacy to maintain a sense of individual identity, and, perhaps most importantly, the presence of something interesting to look at and think about: novelty, discovery, the ongoing engagement with something that has not been fully understood. Neptune and Triton provide this last element in abundance. The scientific richness of the Neptunian system means that there will always be something new to observe, something unexpected to explain, something that does not match the models and demands investigation. The crew will not be bored, not scientifically. They will be perpetually engaged with phenomena that no one has ever observed before, answering questions that have never been answered, conducting science at the frontier of human knowledge. In the history of exploration, the people who have thrived under extreme hardship have almost universally been the ones who are genuinely, personally, passionately engaged with the purpose of their presence in the difficult place. But the social dimension is not solved by scientific engagement alone. The crew must function as a genuine community, one that can sustain shared life across years and decades, that can absorb internal conflict without fragmenting, that can maintain genuine affection and respect for its members, even through the inevitable periods of irritation and disagreement that long-term intimate proximity produces in any group. The selection process for this crew is, in some ways, more like selecting life partners than selecting employees. The mission psychologists and crew compatibility analysts who plan such a mission would need to evaluate not just individual psychological profiles, but the specific group dynamics of potential crew combinations, the interpersonal chemistry that predicts whether a particular group of people can genuinely function as a long-term community. This is not a problem with a clean technical solution. It is a human problem that requires human judgment, and getting it wrong, sending a crew combination that turns out to be psychologically incompatible, could doom the mission regardless of how perfectly everything else was designed. Chapter 8. Should we send them? The ethics, the argument, and the answer. We have now traced the full arc of what a crewed Neptune mission would involve, the distance that puts it 10 years away, the propulsion technology that is necessary but not yet operational, the physiological deterioration that would transform the crew during transit, the fuel arithmetic that makes return essentially impossible, the science that justifies the sacrifice, the communication delay that severs the crew from Earth in any functional sense, and the psychological demands that would test the deepest resources of human resilience. The question we have been building toward is, should we do this? Is it ethical to send human beings on a permanent one-way mission to the edge of the solar system? And if it is ethical in principle, is it the right thing to do given all the competing claims on the resources and attention of human civilization? The ethics of one-way missions. The ethical case against one-way missions rests on a specific premise, that it is wrong to send people somewhere from which they cannot return, because their ability to consent to the full consequences of their decision is limited by their inability to fully comprehend, from a position of safety on Earth, what permanent isolation actually feels like over years and decades. A person who enthusiastically volunteers for a one-way Neptune mission at age 35 might, at age 50, 10 years into the voyage, feel profoundly differently about what they agreed to. The consent given in advance, before the full experiential reality of the mission was known, might not be binding in any morally meaningful sense. This is a genuine ethical concern, but it is not unique to deep space missions. Medical decisions made for potentially terminal conditions involve consenting to ongoing circumstances that the person cannot fully foresee. Religious vocations that involve withdrawal from ordinary social life involve consent to future deprivation. Military service, mountain climbing, polar exploration, and many other human activities involve consenting to risks and hardships that cannot be fully imagined in advance. We do not generally consider these activities unethical, simply because the consent cannot be fully informed about the experiential details of the hardship. The ethical case for one-way missions rests on the combination of genuine consent, meaningful purpose, and the right of individuals to make meaningful choices about the use of their own lives. A person who chooses, with full awareness of the available information about what the mission entails, to spend their life doing science at the edge of the solar system, rather than living an ordinary life on Earth, is exercising a form of agency that we should, in a free society, be prepared to respect. The life at Neptune is not obviously worse than a life on Earth. It is different. It is isolated in ways that are genuinely extreme, but it is also filled with scientific purpose, with genuine discovery, with the knowledge that you are doing something that no human being has ever done. Whether that trade is worth making is a personal decision, and different people will make it differently. The ethical argument is strengthened by the observation that the mission is not simply for the benefit of the crew, it is for the benefit of all humanity. The scientific knowledge generated by a permanent Neptune mission about ice giant planets, about ocean worlds, about the outer solar system, would advance human understanding of our place in the cosmos in ways that will matter for centuries. The exploration of Neptune is not a luxury. It is part of the ongoing project of understanding where we are, how our solar system works, and what possibilities exist in the universe beyond Earth's comfortable gravity well. The survival argument. There is a more pragmatic case for deep space exploration, of which a Neptune mission is a part. Humanity currently exists on a single planet around a single star. This is, from the perspective of long-term species survival, an extremely precarious situation. The risks to Earth, asteroid impact, supervolcanic eruption, pandemic, nuclear war, climate catastrophe, and various other low-probability but civilization-ending possibilities are not zero on any timescale longer than a few centuries. A civilization that remains confined to one planet is one that has a single point of failure. The development of genuine multiplanetary presence, the ability to sustain human life on multiple worlds and eventually around multiple stars, is the most effective long-term strategy for civilizational survival. Mars is the next obvious step. But beyond Mars, the gas and ice giants of the outer solar system represent resources and scientific knowledge that a growing interplanetary civilization will eventually need. Neptune's system contains abundant nitrogen, water ice, and organic chemistry. Triton is a potential base for operations in the outer solar system. Understanding these resources and learning to live in Neptune orbit is a step on the long ladder of expanding human presence beyond Earth. A permanent Neptune mission is not just science for its own sake. It is the rehearsal for a kind of civilization that does not yet exist, but that must eventually exist if humanity is to have a future longer than the next few centuries of geological luck. The crew that accepts permanent residence at Neptune is not simply sacrificing themselves for scientific knowledge. They are pioneering a mode of human existence that all of us will eventually need to embrace, the mode of living on other worlds, separated from Earth not by choice alone, but by the physics of interplanetary distances that make casual return impossible. The historical pattern. Human beings have been sending people to places from which they might not return, for the entirety of recorded history, and likely for the entirety of human prehistory. The first people to cross the land bridge into the Americas did not know whether they could return. The first Polynesian navigators to sail toward the horizon in outrigger canoes knew that some fraction of them would not survive. The first humans to descend into deep caves, to climb high mountains, to sail in open boats across open oceans, all of them were engaging in the same basic human activity that a Neptune mission represents, going somewhere that has never been reached, accepting the consequences of the going in service of the needs and curiosities of the species. What distinguishes the Neptune mission from these earlier explorations is the explicitness of the one-way nature, the duration of the isolation, and the level of technological and physiological challenge involved. But the psychological and ethical structure is the same. explorers have always accepted costs that would be unacceptable to most of their contemporaries in exchange for the experience of being the first. The first humans to reach Neptune will be no different. They will be different, however, in one respect from all previous explorers. They will know, in a way that earlier explorers did not know, exactly what they're getting into. Not perfectly. No one can perfectly anticipate what 10 years in deep space will feel like. But with the benefit of decades of space medicine research, of psychological studies of isolated crews, of careful mission design that takes their welfare seriously, they will go not in ignorance but in knowledge, which is perhaps the most meaningful form of courage. Conclusion. The blue planet at the edge of the solar system is one of the most beautiful and most mysterious objects in the solar system. Its deep, saturated blue is the colour of something ancient and cold and strange, something that has been there for the entire history of the solar system without being properly seen, properly understood, or properly visited. It has one moon whose geysers erupt through ice, whose surface shows evidence of an active interior, whose chemistry hints at possibilities that astrobiologists find genuinely interesting. It has a magnetic field that makes no sense given everything we know about how planetary magnetic fields work. It has wind speeds that no known atmospheric model correctly predicts. It is, in the language of science, one enormous open question. To answer that question properly, to understand Neptune and Triton the way we are beginning to understand Mars, the way we understand the Moon, the way we understand Earth, requires human beings to be there. Not because robots cannot do useful science, but because the specific nature of the scientific questions that Neptune poses, combined with the communication delay that makes real-time robotic control from Earth impractical, makes a crewed presence the only approach capable of achieving the kind of scientific depth and flexibility that the system deserves. The people who go to Neptune will go knowing the full cost. They know the transit time, they know the radiation dose, they know the physiological changes the journey will impose, they know the 8-hour communication delay, they know that the return journey in any practical sense is not part of the mission architecture. They know that the world they leave will be substantially different from the world they are leaving when they finally become old enough and slow enough to look back on what they did and understand it fully. They will go anyway, and in the way that all the great explorations have enriched the collective human understanding of where we are and what we are, the Neptune mission will enrich ours. The scientists who analyze their data from 8 light hours away, the students who grow up knowing that there are human beings at the edge of the solar system, the civilization that gradually extends its presence from Earth to Mars to the outer planets, to the stars, all of them will be changed by what those first humans find and report from the blue planet at the edge of everything we have ever called home. The first humans to reach Neptune will look down at the deep blue sphere beneath them, at the banded clouds moving faster than any wind on Earth, at the dark spots and the bright plumes of Triton's geysers in the distance, and they will know something about the solar system that no one has ever known from that specific vantage point. They will send their findings back to Earth, 8 hours behind every transmission, and they will wait 8 hours for acknowledgement, and then they will go back to work. They will not be coming back, but the work will last long after them, and the blue planet will have been finally visited properly. The daily reality, what life at Neptune would actually look like. There is a dimension of the Neptune mission that tends to get lost in discussions of propulsion and physiology and ethics, the texture of daily life at 30 astronomical units from the Sun. Not the dramatic moments, the arrival, the first glimpse of Neptune from close range, the first landing on Triton. The ordinary days which would make up the vast majority of the mission's duration, and which would determine whether the crew survived psychologically as well as physically. Let us imagine a specific day, perhaps 3 years into the mission. The crew has been in Neptune orbit for several months. The initial excitement of arrival has settled into the rhythm of ongoing operations. Neptune fills a significant portion of the sky from the spacecraft's observation deck. Not the abstract blue point it was during the transit, but a visible disk, banded and textured, with a storm system tracking across the southern hemisphere that the crew has been monitoring for weeks. Triton is visible as a small bright disk against the darkness. The crew wakes to schedules calibrated not to the Sun, which at Neptune is merely a very bright star, providing roughly 1/900th of the light and heat it provides at Earth. but to an artificial day-night cycle maintained by the spacecraft's lighting system. Circadian rhythms in the absence of a meaningful solar cycle require deliberate management. Without careful light scheduling, the crew's sleep patterns would drift and fragment in ways that would compound the existing cognitive challenges. Morning communications review. A batch of messages that arrive during the crew's sleep period, each one sent from Earth 4 hours ago. There are scientific instructions from mission control, suggestions for where to point instruments, questions about yesterday's observations, requests for additional data on a specific atmospheric feature. There is personal correspondence, a message from a crew member's sibling describing a family gathering that happened while the crew was sleeping, a scientific paper from a collaborating research institution asking for the crew's observations to be compared with a new model, news from Earth, political events, scientific discoveries, cultural happenings that the crew learns about 4 hours after it happened, which is functionally contemporaneous on a geological timescale but humanly significant. The crew composes responses. These will leave the spacecraft now and arrive on Earth in 4 hours. If the recipients respond immediately, the replies will arrive at Neptune in 8 hours. More likely, the responses will arrive the next day or the day after, fitting into the asynchronous rhythm that characterizes all Neptune-Earth communication. Work begins. The primary scientific operations for today involve deploying a new atmospheric probe into Neptune's cloud layer, a small instrumented package that will descend through progressively denser layers of the atmosphere, measuring pressure, temperature, wind velocity and chemical composition before being crushed by the pressure at depth. The crew in the command module manages the deployment, while the science team monitors the probe's descent in real time. Real time here means that the probe's data arrives at the spacecraft with essentially no delay. The probe is nearby. The Earth-based scientists who are co-investigators on the mission will receive the data 4 hours later, analyze it, and send observations and questions 4 hours after that. In the afternoon, the artificial afternoon, the time block that the crew has come to associate with afternoon, through the consistent scheduling of the light cycle, a crew member goes to the exercise module for their mandatory 2-hour workout. The rotating habitat provides 0.5 G, which mitigates bone and muscle loss, but the exercise regimen is still required to maintain cardiovascular health and supplement the limited gravitational loading. The exercise module contains the best view from the spacecraft, a large transparent panel looking outward, away from Neptune, into the deep black of the outer solar system. The Sun is visible as a bright star. Earth, at this moment, is more than 4.5 billion kilometers away and cannot be individually distinguished from the stellar background without instruments. The evening is structured around the crew's communal meal, a design requirement of the mission, not merely a convenience. Long-duration isolation research consistently shows that shared meals are among the most important daily rituals for maintaining social cohesion in confined groups. The conversation covers the day's work, the atmospheric probe's descent, a disagreement about interpretation of last week's magnetic field measurements, plans for the upcoming Triton surface sortie. The conversation is specific and engaged because the work is specific and engaging. There is always something new to discuss because there is always something new being observed. Late in the evening, there is a community hour, a period of shared non-work activity that might involve films from Earth, music, games, or simply unstructured conversation. This period is scheduled, but its content is flexible, responding to the crew's psychological state and social needs on a given day. The mission's psychology support team on Earth, monitoring regular crew evaluations and behavioral indicators, suggests specific activities when patterns suggest particular crew members are under elevated stress. Their recommendations arrive 4 hours after they are sent, which is often timely enough to be useful. Sleep, and then the cycle begins again. This is the texture of the ordinary days, and it's important to hold both things in mind simultaneously: the ordinariness of the daily rhythm and the extraordinariness of the context in which it occurs. Neptune filling the sky, Triton visible. The data arriving from the deepest planetary system humanity has ever directly investigated. The knowledge that the nearest other human being who is not on this spacecraft is 4 hours away at the speed of light. The mission is mundane and transcendent simultaneously, in the way that all meaningful work is mundane in its daily practice, while being significant in its cumulative achievement. The crew that endures years of ordinary days at Neptune is in the aggregate, doing something extraordinary, building the base of knowledge that will inform planetary science for generations, extending humanity's physical presence to the edge of the solar system, and demonstrating that human beings can live and work at distances that the entire previous history of space exploration had never reached. The Triton's surface operations, the closest thing to another world. When the crew finally sets down on Triton, which would likely require a specialized lander given that the moon's surface conditions are extreme even by outer solar system standards, they will be experiencing something with no parallel in any previous human exploration. Triton's surface temperature is approximately -235 degrees Celsius, the coldest of any well-characterized body in the solar system. Its thin nitrogen atmosphere is barely detectable by most standards. Its gravity, at 0.08 g, is so low that a crew member in a spacesuit weighs about 8 kilograms, the equivalent of carrying a small bag of groceries. Movement in such low gravity requires adjustment. Normal walking is impossible, and any uncontrolled movement could launch a crew member far off the surface. The landscape of Triton, from the Voyager 2 flyby images, is strange and beautiful in equal measure. The cantaloupe terrain, rounded dimples and ridges formed by convective overturn of the icy crust, extends across much of the surface. Polar nitrogen ice caps reflect sunlight. The dark streaks of the geyser deposits stretch downwind from their sources. There are smooth plains that suggest ancient flooding by liquid or slush material, and there are regions of extreme topographic relief that indicate active or recent geological processes. Standing on Triton's surface, the crew would experience conditions utterly unlike anything on Earth or Mars or the Moon. The sun, visible overhead, would be a bright star rather than the disk that provides warmth and light to the inner solar system. Neptune itself would dominate the sky, a massive blue and white sphere several degrees across, looming in the darkness, its storms visible as dark patches against the banded clouds. The silence would be absolute, or almost absolute. Triton's thin atmosphere is not completely without sound-conducting capacity, and the low-frequency rumble of geyser activity might be detectable by sensitive instruments, if not by the human ear through a spacesuit. The crew's work on the surface would be the kind of hands-on investigation that robotic missions can only approximate, collecting samples from different surface terrains, deploying seismometers to monitor internal activity, examining geyser vents to understand what is being erupted from below, and looking for signs of any chemistry that might indicate subsurface biological activity. This last objective would be approached with the same careful protocol as any planetary protection mission, the strict avoidance of any contamination of potential life-bearing environments with Earth biology. But the possibility, however remote, of finding signs of life in a Triton subsurface ocean would inform every sampling decision. The surface sortie would be limited in duration by life support constraints and by the physiological adaptability issues of a crew that has spent years in partial gravity adapting to Triton's extreme low-gravity environment. But even a few extended sorties, conducted over the months of Neptune orbital operations, would produce more direct scientific knowledge about Triton's surface than any robotic mission has ever achieved. And the data from those sorties, the samples, the seismic records, the chemical analyses, would be transmitted to Earth and to the broader scientific community, becoming the foundation of Triton science for the next generation. Thanks for watching.